The universe began with a colossal bang, and it's been growing, changing, and surprising us ever since. Picture a pinhead-sized clump of heat that suddenly goes boom, and everything, light, air, oceans, pizza toppings, your favorite jeans, finds a way to exist. The space around it stretches like bread in a warm oven, cooling as it grows, turning chaos into order. Galaxies become glittery islands in a cosmic sea, stars pop on like sparkler notes, planets drift by on invisible strings. We'll keep it simple, no heavy math, just pictures you can imagine and a few friendly jokes to keep it light. This is the big story that connects your morning routine to the dawn of time, from the Big Bang to the end of time. Along the way we'll use easy comparisons, popcorn popping, coffee cooling, a sunrise that never ends in a single day, and yes, a few goofy moments to help it land. Watch, because understanding this grand arc helps us see our own little moments in a universe that's huge, ancient, and wonderfully strange. The Big Bang, a fireworks kickoff. The Big Bang marks the start of the universe as we know it, not an ordinary explosion in space but the moment space itself began to grow and carry along all the energy and matter that would ever be. It happened about 13.8 billion years ago. In that instant, everything was incredibly hot and dense, like a cosmic kettle at full boil. The moment of the Big Bang can feel like a grand sparkler lighting up the room of nothing, a fireworks kickoff that nudged everything into motion. Light had nowhere to go at first. As the universe stretched and cooled, that light finally found room to travel, racing outward and painting the newborn cosmos with tiny glimmers. There is a famous afterglow from that time, the cosmic microwave background, a faint, chilly glow that scientists measure with special instruments and call a baby photo of the universe. It's a glow we still see everywhere. Imagine a warm sunrise that has been stretched into a long, cool whisper as the universe grew. That's what this light is like in reverse. Gravity then began peeling matter into clumps, much like people huddling around a campfire, and from those clumps the first stars started to shine. Those early stars lit the way. From those early sparks, more complex structures formed, galaxies, clouds of gas, and eventually planets, until the stage was set for everything we see today, all sparked by that fireworks kickoff. A grand start, one bright push that carried us all forward. Inflation, the universe's growth spurt. Inflation is a theory about a brief, dramatic growth spurt in the early universe. In the moments after the Big Bang, space-time stretched enormously in a fraction of a second. Put plainly, the universe doubled, tripled, and kept expanding so fast that distant regions could end up sharing the same temperature and properties. This helps explain why the night sky is so uniform and why space looks flat on large scales. Blowing up a balloon this fast would press distant patches together before any bumps could form. The result is a smoother cosmos. Before inflation, some puzzles bothered cosmologists. If the universe had grown slowly, hot and lumpy regions would be obvious when we look far away. Inflation acts like a cosmic eraser and a space fix-it. It smooths out wrinkles and makes the overall geometry look flat, like a perfectly leveled table. That helps align many observations. It also helps keep exotic leftovers, like heavy particles, from piling up in odd places. The idea is that a tiny region of space swelled to cover huge swaths of the cosmos. That growth spurt is what made the map of the universe easier to read. While inflation happened, tiny fluctuations in energy and density were carried along and stretched to enormous sizes. These fluctuations started as whisper-thin ripples, the kind you barely notice on a pond when a breeze passes by. As space blew up, these ripples grew into the seeds of structure, the places that would later become galaxies, stars, and clusters. In the cosmic fossil light we call the cosmic microwave background, we can still see that pattern, faint twinkles that mirror the original bumps. It's as if a chef sprinkled seeds into dough and the dough puffed into air pockets that later became bread. Scientists test inflation by looking at the cosmic background light, the afterglow from long ago. The pattern of tiny temperature differences across the sky matches what inflation predicts, a smooth universe with a splash of small bumps. Some experiments chase a special fingerprint called polarization patterns, which would hint at gravitational waves from that growth spurt. If seen, it would be strong evidence that inflation happened. But even without that signal, many inflation models fit the data and remain the leading idea. The details vary, but the core idea stays: a brief, explosive stretch set the stage for everything we see today. It's like a cosmic version of laying the carpet with a laser level, perfectly flat, minus the claustrophobic glue smell. Primordial soup, quarks, gluons, and nuclear beginnings. Right after the start, the universe was a blazing, crowded broth where quarks zoomed around and gluons carried the strong force like tiny invisible helpers. There were no atoms yet. Quarks are the smallest pieces we know, and gluons are the glue that keeps them together and the shuttle service that nudges them into shapes. It was a busy, hot kitchen with rules even in chaos. In this soup, particles popped in and out of each other, constantly changing who was friends with whom. In this quark-gluon stage, quarks can roam freely, not stuck inside protons or neutrons. Gluons keep them linked when they choose to pair up. The heat acts like a strict teacher, making the strong force swing into action, holding teams together and letting them swap players without losing the game. It's a wild, orderly dance. You can picture it like a crowded ballroom where people keep moving, yet the music pushes some pairs to stick close while others drift apart. As the temperature eases a bit, quarks begin to pair up into protons and neutrons. These are the makers of the nucleus. 3 quarks combine to form each proton or neutron, with gluons still tagging along as the glue. They start stacking into tiny bundles called nuclei. With further cooling, the first light nuclei appear, like hydrogen and helium pieces, arranged much like beads on a string, ready to be joined into longer structures. These early nuclei are the seeds of chemistry, waiting for electrons to join and make atomic atoms. When electrons come along, light can travel freely again. All this happens before stars exist, in a quiet phase where the universe becomes a little less hot and a little more like the clockwork that shapes our everyday materials. It's the moment when soup cools enough to braid particles into the first elements. And even though it's hard to picture, this primordial work sets the stage for everything else that follows, from the glow of distant galaxies to the batteries in our phones. Recombination and the cosmic microwave glow. Long after the Big Bang, the universe cooled enough for electrons to join with nuclei and form neutral atoms, the moment we call recombination, when light finally found a way to travel. That moment freed light. Before it, photons bounced off free electrons like a crowded hallway, making the universe opaque. Space finally grew quiet. When recombination happened, the cosmos became transparent and photons began to sail outward, unhindered for the first time. The oldest light we can still see is this glow. As the universe expanded, that light cooled from about 30 Kelvin to a chilly 2.7 Kelvin. Today it fills the sky as a faint glow. The glow is microwave light spread nearly evenly, a near-perfect black body signal, like a plain white sheet with a whisper of warmth. In plain words, it's light that has stretched as the universe grew. Tiny bumps in that glow encode where matter clumped early on, the seeds that would grow into galaxies, stars, and planets. Scientists read those bumps with careful instruments. We measure the glow with satellites and ground telescopes, turning minute temperature differences into maps of the early cosmos. Those tiny patterns are cosmic fingerprints. The glow sits at about 2.7 Kelvin today, its photons stretched into the microwave range by the universe's expansion. It's like finding frost on a window that tells you about last winter's weather. Dawn of structure, from smooth to spotted cosmos. The early universe started almost perfectly smooth, a vast, even soup with only the faintest ripples. Tiny bumps broke the uniformity. These little variations acted like seeds, waiting for gravity to do its stubborn job. Think of a loaf of bread cooling on the counter, where a few sugar grains settle into a few spots and stay. Gravity is patient and stubborn. It kept pulling on those bumps, and the bigger ones grew faster while the tiny ones stayed quiet, like background noise. Dark matter, unsighted stuff, did most of the heavy lifting, forming a faint skeleton for the universe to cling to. Gas followed that scaffold, cooling and gathering until clumps grew heavy enough to shine with starlight. The first stars poked through the fog. These newborn suns lit up their neighborhoods and pushed gas to settle into spinning disks and clumps. In simple terms, structure moved from smooth to spotted, like a quiet field turning into a dotted landscape. This marks the dawn of galaxies, moments when the world learned to organize itself. Today we still see the fingerprints of those early clumps. The cosmic web stretches like a giant spider's net, with bright galaxies sitting along the threads. We glimpse the microwave glow of ancient light, a baby picture of the bumps that later grew into stars. From smooth to spotted, the universe found a way to turn a wild recipe into a grand kitchen of galaxies. The first stars, lighting the cosmic night. In the earliest moments after the Big Bang, the cosmos was a hot, thick fog where light and matter jostled together and could barely travel. As the fog cooled, stable atoms formed, mostly hydrogen and helium, like the first beads on a string. Under gravity, these gas atoms began to slide toward each other, gathering into small clumps. The clumps grew heavier, pulling in more gas, until they became seeds for something new, a scene of quiet potential ready to snap into light. Within these clumps, gravity pressed gas tighter and hotter. The temperature rose until hydrogen began to fuse into helium, a tiny engine waking up inside the core. The first stars lit up the cosmic night, huge and bright, their glow pouring ultraviolet light into the surrounding fog. The light pried open bubbles around the stars, ionizing the fog and pushing it aside, like turning on a lantern in a dark room. The newborns burned fast, with bright lives and hotter tempers, more blaze than patience, like a campfire that forgot to smolder. As they shone, these stars forged the raw elements in their cores. When they ran out of fuel, many exploded as brilliant supernovae, scattering heavy elements far and wide. This enriched gas became the ground for future stars and planets. Without it, there would be no rocky worlds, no oceans, no life as we know it. So the first stars did more than light the night, they prepared the ground for everything else. From this moment, the universe began to glow with many twinkling cities, small galaxies forming, new stars born from leftovers gas, and the cycle of birth and death continuing. The first light was not a single sunrise, but a chorus waking up the cosmos. If you stand under a clear sky, you can almost hear that moment, a handful of bright sparks breaking the darkness, hinting at the vast, bustling orchestra of lights that would follow. The cosmic night turned into a painted horizon, speckled with the first suns, teaching us that light travels far and can change everything it touches. Element making in stars, hydrogen to iron. Stars begin by turning hydrogen into helium in their cores. Hydrogen atoms collide and, with a touch of physics, 4 protons end up as a helium nucleus and some energy slips out as light. That energy is the star's fuel for warmth and glow. The process happens because the core is extremely hot and squashed by gravity, making particle collisions frequent enough to fuse. When the hydrogen runs low, the core tightens and heats further, pushing the star to the next stage. With hydrogen mostly gone, the core contracts and heats up more. Helium nuclei then fuse to form carbon. In a simple way, 3 helium atoms join to make a carbon nucleus. Occasionally, a carbon nucleus grabs another helium and becomes oxygen too. This helium-burning stage keeps the star shining and changes its internal balance, as new fuel is found in the heart. It's a bit like baking bread in a hotter oven, where the recipe makes a sturdier loaf and a few extra flavors appear. The star feels the change and holds steady for a while. After helium fuel fades, the core grows hotter still and begins fusing carbon into heavier elements. Carbon burning can create neon and magnesium, and later oxygen burning can produce silicon and sulfur. Silicon burning pushes the core toward iron when it all settles down. The furnace is now in full multi-layer mode, with shells of different fuels surrounding a core of new elements. It's a cosmic onion, each layer built by a fusing story, one after another, with heavier elements in the center. The star's heart is stacked with new chemistry, ready for the next big act. At last, iron sits at the center and fusion there no longer releases energy. Without energy to counter gravity, the inner part of the star succumbs and collapses, while the outer layers may blow away in a spectacular finale. The star leaves behind a dense core and seed space with iron group elements and other heavy stuff that later become parts of planets and even life. In this way, the life of a star shapes the ingredients for everything we breathe, see, and touch. Supernovae and the seeds of life. When massive stars run out of fuel, they end their lives in a brilliant explosion called a supernova. The blast throws out lots of heavy elements into space. Stuff like carbon, oxygen, and iron mix with stardust to become part of new suns and planets. A cosmic recipe spreads. Nucleosynthesis is just a fancy word for making new atoms in a star. Inside the star, light elements fuse into heavier ones, and when the star dies, a supernova blasts these elements outward. That rain seeds dust that becomes a new sun. It is as if the universe is recycling leftovers into fresh neighborhoods. Planets grow from rings of dust and gas around new stars. If those clouds carry water and organic molecules, life can begin. Chemistry in the right mood makes complex molecules that can become building blocks for cells. Some life may be simple at first, like tiny microbes that can survive on salt or heat. Even here on Earth, scientists find clues that life's building blocks arrived by meteors and comets. That connection to supernovae gives a cosmic wink to our own origin. Every new star and planet carries a hint of the old supernova. By lighting up space and spreading elements, supernovae help grow kitchens for life across the cosmos. The seeds of life are not a single spark but a slow drift of dust, gas, and time. We may be living in a universe that keeps mixing ingredients, with a little humor baked in. And if we look up, we can imagine future worlds where those seeds become vines, roots, or maybe microbes beneath alien suns. The galactic web, filaments, clusters, voids. On the largest scales, the universe isn't a random sprinkle of galaxies. Instead, galaxies line up in a vast tapestry called the cosmic web. This web is made of filaments, clusters, and voids. Galaxies ride along the filaments, gather in clusters, and many regions are left empty as voids. Understanding this web helps explain why galaxies grow differently in different places. Think of it like a city grid with roads, town squares, and empty lots. The filaments are the roads, the clusters are busy centers, and the voids are quiet neighborhoods. The whole structure grows from tiny density fluctuations after the early universe and the pull of gravity over billions of years. Filaments are like cosmic highways. These threads stretch across huge distances, linking major hubs. They are built from dark matter and ordinary matter, and they carry galaxies, gas, and invisible gravity. Matter flows along these channels as gravity pulls toward heavier regions. If you were a tiny explorer, you'd drift with this flow, gathering material as you go. Filaments form the backbone of the web, a grand network that guides cosmic growth. Imagine strings connecting beads across a giant map, that's a filament. Along these highways, nothing is perfectly straight, yet the overall direction is clear. Where filaments meet, clusters lie. These are the busiest neighborhoods, packed with many galaxies. Gas in clusters gets hot and shines in 10th ray light, like a street lamp in a fog. Stars form, but the crowded setting often ruffles dusty clouds and slows creation of new stars. The Milky Way sits in a larger neighborhood called the Laniakea supercluster. Galaxies tug at one another there, trading gas and sometimes merging. Gravity keeps the cluster together, shaping the galaxies over time. Clusters act like cosmic roundabouts where traffic from many filaments converges. Voids are the spacious empties of the map. They span huge distances with very few galaxies. Gravity pulls matter away from the emptier regions, leaving them dark and quiet. Galaxies that live in voids tend to be smaller, more isolated, often with a slower life. In busy filaments and clusters, interactions and mergers are common, which can spark bursts of star formation or shuffle galactic shapes. The cosmic web shows why galaxies come in different forms, from spirals to strange, lumpy kinds. Looking at the web is like reading a city map written in space, where roads, centers, and empty blocks tell the story. This dynamic structure continues to evolve as gravity slowly rearranges matter across the cosmos. Our Milky Way, a spiral in a cosmic sea. The Milky Way is a vast spiral of stars, gas, and dust, a grand celestial pinwheel that we ride through on day and night. It spans a huge distance, so large that a traveler would need many lifetimes to cross. Inside this spinning disk, stars gather in wispy arms, like luminous rivers winding through a cosmic countryside. Our sun sits in one of those arms, happily away from the glow of the center. In the Milky Way, the glow comes from countless suns sharing space with clouds of gas that give birth to new stars. Think of it as a city where new neighborhoods pop up as people move in. Dust and gas act like kitchen ingredients that someday become a sparkling bakery of stars. Sometimes you can see bright patches where stars are forming, like fresh bakeries opening in town. At the heart lies a busy middle, a region where a huge black hole called Sagittarius A** quietly sits and gathers light and matter. It is not a monster you can bargain with. The spirals themselves are not fixed fences but flowing arms where stars travel along paths, weaving a graceful, slow dance. Along these arms you find star factories and stellar nurseries. Our Milky Way moves through a sea of dark matter and faint gas, a background that holds the galaxy together. We ride a circular path around the center. Over time, the Milky Way will meet its neighbor Andromeda in a slow embrace that reshapes both of us. Until then, we keep watching, telling stories of comets, meteors, and the glittering spiral we call home. Dark matter, the hidden scaffold of space. Dark matter hides in the shadows, and we can't see it with ordinary light. It is the invisible skeleton that holds galaxies together. If the universe were a building, dark matter would be the unseen studs behind the walls. It doesn't glow or shine, and it hardly ever bumps into ordinary matter. That quiet behavior makes it tough to catch, but scientists keep looking. We infer dark matter from gravity's tug. Stars near the edges of galaxies orbit as if there is more mass there than we can count. We also see light bent by gravity, like a magic mirror, revealing hidden mass. This bending is called gravitational lensing. Even the glow of the early universe carries clues about how matter clumped together. Scientists build computer maps of gravity to see where extra mass must be. They compare what we see with what gravity would do if only visible matter existed. If the math demands more stuff, that extra stuff is dark matter. It's the prime suspect behind many cosmic puzzles. People search for the particle behind dark matter. Some ideas imagine shy particles that rarely bump into normal matter, like quiet neighbors who never say hello. Others talk about a field that changes how gravity acts on small scales. Some hints come from candidates such as very shy particles or little waves in a field, descriptions that want to keep things simple. Underground detectors and faraway telescopes are listening for whispers from dark matter. While the mystery continues, dark matter remains the hidden scaffold that shapes the cosmos. Dark energy, the universe's slow expansion. Across the vast quiet of space, a kind of energy sits in the background, pushing on nothing and everywhere at once. We call it dark energy. It isn't something you can touch, yet it acts like a gentle breeze that keeps nudging the universe to grow. Picture space as a balloon slowly inflating, and imagine dark energy as the unseen air quietly urging it to expand. Dark energy doesn't push on planets the way a friend nudges a swing, it makes the fabric of space itself stretch. That stretch carries galaxies along like dancers in a long, slow waltz. The rate at which space expands can change, and when it does, the cosmos grows a little emptier and cooler to the eye. In everyday life terms, it's a slow, persistent tug on the carpet of reality, the cosmic version of a roommate insisting the living room must be bigger even if the couch stays in place. Imagine galaxies as raisins in dough. As the dough rises, the raisins drift apart simply because the space between them grows. We see light from faraway galaxies born in that widening space becoming fuzzier and more stretched as it travels toward us. It's like listening to music through a wall that keeps moving away, the song will sound more drawn out over distance. The whole scene feels peaceful, but it hides a powerful push behind it. Scientists study dark energy by watching many galaxies and the glow of distant starlight. They piece together how fast the stretch happens without needing to see it directly. Some ideas say dark energy acts as a constant background push, others wonder if it could change over time like a mood. For now, it remains mysterious, cozy in a way, and crucial to what the universe might become. If the expansion keeps going, the cosmos would drift farther apart, stars would fade from sight, and the night would get very quiet and very cold. The end of time, in this view, isn't a bang, but a quiet, endless spreading that reshapes what can be seen and what can still touch us. Stellar life cycles: birth, burn, die, recycle. Stars begin their lives inside cold, shadowy nurseries called nebulae, where gas and dust drift like mist. Gravity pulls it in. The core grows hotter until hydrogen fuses into helium, lighting up the cloud from the inside like a tiny furnace waking up. Fusion is the spark. A newborn star then settles into a steady glow, a quiet engine that can power a whole neighborhood of planets for eons. For most stars, life on the main stage means burning hydrogen steadily, keeping the sun-like furnace burning. It lasts a long time. When hydrogen runs low, the core shrinks and the outer layers puff out, turning the star into a red giant with a big, ballooning belly. The change is dramatic. Then fusion reaches heavier stuff in the core and the star sheds its outer cloak, creating a glowing shell called a planetary nebula, while the inner ember fades to a fragile white dwarf. If the star is massive, the ending is a fireworks display called a supernova, blasting heavy elements far into space. That blast seeds the next generations. What remains can be a neutron star, an incredibly dense tiny city of neutrons, or a black hole, a gravity trap from which nothing, not even light, can escape. Both are stark endings. But even these endings are not the end of the story, because their debris mix into the cosmic soup that feeds new stars. The leftovers from white dwarfs, red giants, and supernovae mingle with gas and dust to form fresh clouds that may birth new suns and worlds. Recycling keeps the galaxy alive. In this grand kitchen, stardust becomes the stuff of planets, oceans, and even life, a reminder that endings can nourish beginnings. the universe does not waste a bite. So the birth of a star, its steady burn, a dramatic death, and the recycle of its remains weave a timeless loop that keeps the cosmos growing, glowing, and surprisingly playful as it tumbles through time. Nebulae, the cradles of future suns. Nebulae are vast clouds of gas and dust floating in space, the raw stuff from which stars are born. They come in different kinds. Some glow with the light of newborn stars, while others block the light like space fog. The Orion Nebula is a well-known example. In these giant nurseries, gravity slowly pulls particles together, turning a cloudy mist into clumps that can become stars. Inside a cloudy nursery, gravity does the heavy lifting. Small grains of dust stick as they collide, much like how kitchen flour dust gathers when you add a splash of water. As clumps grow, they compress the gas and heat up a little. When heat and pressure get high enough, a new star begins to shine in the heart of the cloud. This early phase is called a protostar, a baby star impatient to glow. The cloud also feeds forming planets. Around young stars, spinning disks of gas and dust swirl. In time, bits of rock and ice bump together to make small bodies, and those can grow into full-blown planets. It's a messy, slow process, but it happens in many places. Life on Earth had a similar origin story, a long dance of bits sticking together until a world formed. Nebulae were never quiet. Sometimes a nearby star's explosion or a fast jet from a newborn star cuts through the cloud. It's like space throwing a glitter party, bright and a little chaotic. These events spread heavy elements and light, reshaping the cloud and possibly triggering new stars. Over time, the nebula may fade, or it continues to cradle fresh suns in another pocket of space. The cycle keeps repeating, like a cosmic workshop where future suns are molded. Planets and orbits, from dust to worlds. Planets start as tiny specks of dust that float in a flat, spinning cloud around a newborn sun. The specks stick when they meet. As they cling together, more collisions add up and make bigger rocks, until you have chunky clumps called planetesimals that wander the disk like teens at a mall. The process is messy but patient. These growing worlds sweep up gas and extra material, shaping themselves into rocky neighbors close to the star and bigger, gassy giants farther away. Gravity is the main choreographer in this dance. Planets settle into paths around the star, usually curved and looping rather than straight lines. Some are near circular, others are a bit oval. Gravitational nudges from nearby bodies can tilt or twist a path, or lock two worlds into a shared rhythm, like two dancers stepping in step. Migration can move a planet inward or outward, like a kid sliding on a floor with wheels. What a planet is made of helps where it sits. Closeness to the star bakes rocks into metal and stone, farther out, ices help lumps stick and grow. That's why you find rocky worlds close in and icy giants further out. A bright, chilly layer beyond the inner worlds lets ice stay solid, so bits there can build faster into big planets that wear thick atmospheres. Water can ride along in some areas, making oceans later if conditions stay friendly. The space where planets live is not empty, it's filled with leftover rocks, dust, and icy crumbs that still drift like remnant sprinkles on a kitchen counter. Some of these wanderers become asteroid belts or comet piles. Occasionally a shake or a close pass can nudge a world into a new path, stirring up seasons long after the first day of discovery. Orbits then settle into steady tunes, predictable enough to send scientists to map them and dream of trips. In the end, the orbits hold the planets in their gentle, sometimes wild dances, turning dust into truly known worlds you can visit in stories, games, or quiet nights watching the sky. The Solar System Sketch, a local cosmic family. At the center of our neighborhood sits the sun, a bright parent who keeps everyone close with gravity. The planets and all the smaller members circle around it in a calm, timeless to and fro. The solar system feels like a cozy clan where each member has its own home but shares one big, warm family space. The sun offers light and heat, and without it life on Earth would be a chilly whisper. Near the center, the rocky siblings live up close, small, dense worlds with solid skins. Mercury is the closest, a quick little world that gets roasted by the sun and shaded by nothing much else. Venus wears a thick blanket of clouds that traps heat and keeps the surface mysterious. Earth hosts life and oceans that chatter with plants, animals, and tiny microbes. Mars is a dusty desert, with tall volcanoes and dry valleys that make rovers feel at home. Beyond them drift the big, windy giants, the gas and ice giants who wear thick atmospheres and huge storms. Jupiter is the giant with powerful weather and many moons. Saturn wears magnificent rings like a glittery belt. Uranus tilts on its side, making seasons last a long, peculiar time. Neptune is deep blue and chilly, a windy distant cousin. Out there we meet the colder cousins and scraps of the broken family, the asteroid belt and the icy bodies beyond. Some bits are rocky scraps from a failed planet, while others are icy wanderers that sail outward in long, slow orbits. Distant dwarf planets drift in these outer regions, reminding us the family has many shapes. Comets appear as bright travelers with glowing tails when they visit the inner solar system. The whole clan stays together because gravity is patient and persistent. Orbits are like a family schedule, predictable enough to feel safe but flexible enough to surprise you with a new view. From our own planet, Earth, we are part of this story and see a tiny slice of the family in the night sky. Sometimes the humor of it shows up in how the planets keep a respectful distance, not bumping into each other, as if they're politely sharing a living room for a long, cosmic afternoon. The emergence of life, chemistry, chance, and change. Life begins in chemistry. Tiny molecules drift in warm, watery places, bump into each other, and sometimes stick together to form bigger things. Water acts like a friendly solvent, helping molecules meet and float, while heat and chemical energy push reactions along. Over time, some simple building blocks link up to make polymers, which are long chains that do jobs in cells. Proteins are such chains that can fold into shapes and act as machines. Nucleic acids like DNA and RNA store information and can help guide chemistry, in simple terms. In certain shallow pools or vents, fatty molecules can assemble into tiny bubbles that trap chemistry inside. Chance plays a big role. A lucky arrangement of molecules might produce a self-replicating system, a tiny loop that can copy itself when fed energy. Most attempts fail, but a few succeed and leave behind descendants. Metabolic networks begin to form, meaning sets of reactions that share fuel and waste products, like a tiny factory running on a budget. Membranes give organization. Lipids naturally form bubbly shells that keep reactions together and protect them from wandering into the surrounding water. Inside these shells, chemistry can be controlled enough to produce more complex molecules. Over many small steps, a simple, self-reproducing system can grow into a protocell, a basic unit that can divide and spread. Errors in copying genetic information add variation, and natural selection weeds out the dull and favors the better at getting energy and building blocks. From this point on, life is a dance of change and adaptation. Today, life uses sunlight, chemical energy, and even heat from the earth to fuel its work. A leaf turns light into sugars, a microbe bounces through a hot spring, a bacterium learns to eat new chemicals. The same core ideas show up again and again, simple pieces, lucky accidents, and countless small improvements. If you want a picture, imagine a vast library built from tiny bricks that can copy themselves and rearrange the shelves as needed. Evolution and complexity on Earth. Life began as simple chemical systems that could copy themselves. Over long stretches, these scraps of chemistry settled into tiny cells with a soft interior and a protective skin. Some learned to harvest energy from the sun, others from chemical meals in their surroundings. That basic trick, gathering energy, growing, and making more copies, opened the door to a much larger story. Inside those early rooms, molecules learned to cooperate and form the first real biology. Soon, cells joined into teams and then into true multicellular life. With more parts to organize, bodies could grow bigger, live longer, and do more kinds of work. Some cells became muscles and nerves, others stayed as skin and armor. Think of seaweeds waving on the surface, corals building quiet cities under the waves, fungi threading through wood, and tiny animals making quick trips to catch a meal. Small differences in how parts work together could create shapes as simple as a leaf and as intricate as a hummingbird's beak. Energy keeps the whole web moving. Plants turn sunlight into food and, in the process, fill the air with a breath of oxygen. Animals nibble those plants, others chase the nibbling animals, and scavengers tidy up leftovers. A web of feeding and avoidance forms, with every creature listening to warnings, smells, and touch. Mutations nudge changes, and natural selection favors traits that help survival, like a beetle with a shell that protects it, a fish that dodges a predator, or a plant that twists toward a rewarding ray of light. Practices like camouflage, migration, and cooperation quietly become main characters in the drama. Humans arrive on this stage as a highly capable member of the family, one that uses tools, language, and shared ideas to bend its surroundings. Our brains are flexible, letting us learn, plan, and invent. We shape ecosystems with farms, cities, and gardens, and we keep finding clever ways to live with many other species at once. Bees communicate with dances to share where nectar hides, octopuses solve puzzles with curious hands, and elephants remember friends and places for a long time. Culture grows on top of biology, a layer of knowledge that travels faster than genes alone. That combination fuels new forms of complexity, from social structures to medicines, art, and science. Looking ahead, life on Earth keeps adapting as climates drift and landscapes change. Some species disappear, while others push into new niches and sculpt new relationships. The tree of life keeps branching, sometimes slowly, sometimes with surprising leaps. Humans are part of that ongoing story, shaping environments while learning how to live with the rest of the living world. The future isn't a fixed line, it's a living process of change, resilience, and invention. And through it all, life keeps weaving ever more intricate patterns from simple beginnings, a reminder that even the smallest cell can become something astonishing with time and a bit of luck. Humanity emerges, from cave to cosmos. Curiosity started in the dim light of caves, where sharp stones became knives and spears and hands learned to shape them from bone and rock. With these tools, early people hunted, cooked, and protected kin. Fire changed daily life, turning fear into warmth and light, and giving a simple meal a different flavor. They probably learned quickly that cooking beats cold, rock-hard leftovers, which is a funny kind of upgrade. Caves offered shelter from weather and danger, and walls became a place for pictures and stories. Life was practical, shared, and stubbornly hopeful. Language grew piece by piece, helping friends warn each other about danger, plan hunts, and tell where to find berries. Words carried jokes and memories. Sharing ideas let people remember safe routes and clever tricks for building shelter. Staying near one camp created a tiny town out of skins, stones, and laughter. Over time, farming and domestic animals slowly changed the rhythm of life. Trade made distant colors and shells familiar, weaving networks of exchange across landscapes. Art and marks on walls began to act like memory boards, showing who did what and when to plant. People formed groups with shared work and shared meals. Cities grew, and with them more complex roles, rules, and routines. A new kind of thinking arrived, records, plans, and ideas stored for later. From the loom of daily life sprang questions about why the world works and what lies beyond the visible horizon. Ideas grow. Science started as careful observation of weather, seasons, and the cycles of day and night. Technology followed, turning tools into machines, ships into routes, and telescopes into windows. Rockets and probes later joined the parade, carrying human voices toward the vast unknown. This is the arc of humanity from cave to cosmos, a thread that began with touch and ends in curiosity. Language, culture, and science, a human expansion. Language grows from the need to share, and that basic act opens doors. From the first grunts to the first scripts, people found ways to name things, to warn danger, to tell a joke, and suddenly the world became something you could discuss with a neighbor rather than just endure. Words shape what we notice. Clear speech helps a family cook together, plan a harvest, and raise a curious child who asks why the sky is blue. Even a cat seems to react more to tone than to grammar. Culture is the pantry of shared habits, stories, foods, and rules that tell a group how to live. As people move and mix, recipes travel, dances change, and holidays borrow colors from strangers, turning everyday life into a grand collage. Rules can be gentle. Our senses adjust to custom, the way we greet, how we wait our turn, what jokes land. A handshake can be polite, a bow might be cool, and a nod can mean "first heard you" without words. Laughter travels across kitchens and streets, stitching communities together with everyday rituals. Science is the habit of asking why and checking to see if the answer fits. It starts with simple observations, like noticing rain makes puddles, then tries ideas in small tests, and finally builds bigger explanations that help sail ships, heal wounds, or light up the night. Mistakes are part of the method. People from many walks contribute, because a fresh eye can spot something the old crew missed. Science can be fussy, and experiments sometimes smell like burnt sugar, but the smell is a clue. Technology grows after careful testing, not from a single genius alone. Language, culture, science are the three engines of human expansion. Together they let us share discoveries, spread kindness, and build tools that reach far beyond a single town. Translation helps, but meaning travels with care. A new generation speaks multiple languages, builds bridges with art and code, and finds new ways to ask questions about time, space, and life. If a robot teaches us to bake bread, we will still need a human joke to keep us smiling. The journey continues as long as someone wonders what comes next. Observatories and telescopes, seeing the unseen. Observatories sit on high hills and in remote deserts, their domes opening like quiet eyes toward the night sky. They catch what our eyes miss. From there, scientists gather light from distant stars and galaxies, turning it into pictures and numbers we can read. It's like listening to a city at a distance through a wall of glass. Different kinds of telescopes listen to different kinds of light, from the visible glow we call light to invisible infrared and radio hiss. Earth's air is a mixed bag. Dust clouds in space hide parts of the sky, but infrared light slips through like a hot cup of coffee steam, revealing what lies inside. Adaptive optics act as tiny space critics, correcting wobble in real time. Sending a telescope into space keeps it away from air and weather, giving crisper pictures. The result feels almost dreamlike. Famous space telescopes are patient artists, painting the cosmos with colors that the eye cannot see, especially where heat and cold sing out. They look at deep space and bring secret histories into our labs. The data from these eyes turns into tools that help scientists, doctors, and engineers in everyday tasks, from better weather forecasts to new materials. People around the world can help by classifying images or spotting oddities. A single telescope snapshot becomes a story about planet birth or galaxy dances, turning a dark sky into a picture you want to pin on the fridge. And yes, sometimes the view is so stunning you save a copy for your wall. Light, time, and cosmological measurements. Light is the universe's postcard, carrying details from faraway places to our eyes and instruments. It travels at a fixed speed, but the journey can be so long that we see objects as they were long ago. The first fact to keep in mind is that light is how we witness events that happened in the distant past, not what is happening right now. Time in cosmology behaves like a trick of perspective. When we look at a galaxy, we are looking back in time because the light needed to reach us had to travel across space. This is the look-back time, the idea that the farther away something is, the older the light we see. It feels almost like reading a story in reverse, where the ending arrives long before the page is turned. The practical upshot is that our maps of the cosmos are built from light that already carried its own history. To measure distances and the size of the cosmos, scientists rely on light with predictable brightness or patterns. Some objects glow with a nearly fixed brightness, acting as standard candles and helping us judge how far away they are. A familiar example in simple terms is a light bulb that should shine with the same brightness each time you switch it on, letting you estimate distance by how dim it appears. Other methods look for regular, repeating patterns in the way matter was arranged long ago. These patterns act as standard rulers, letting us gauge scale by how stretched the signal is. Think of it as using the ripples in a pond after a stone lands to judge how far the throw was, but on a cosmic scale. The oldest light we can measure is the cosmic microwave background, a faint glow that is a baby picture of the universe. It tells us about conditions when the cosmos was very young and offers a baseline for how structures like galaxies grew. Modern instruments, from ground-based telescopes to spaceborne sensors, tease out tiny details in this light, and they also study how light from more recent epochs is stretched by the universe's expansion. There are practical challenges, too. Dust, blinking stars, and the quirks of detectors can blur the signal. Scientists tame these issues with careful calibration, cross-checks, and clever data analysis, much like cleaning glasses and comparing notes from different observers. In the end, light and time together let us chart a grand timeline, estimate distances, and test ideas about how the universe evolves, all while keeping a sense of humor about the universe's quirky pace. The expanding cosmos, redshift and the big reveal. Light from far-off galaxies carries a clear message: the universe is stretching. When we split that light into colors, we notice a shift toward the red end of the spectrum. That red shift isn't about light aging on its own, it's the space between us and the galaxy growing as the light travels. Imagine tugging a sock on a string as the distance widens, the light's waves get longer too. The picture forms slowly, like a film reel played in a quiet theater. The big reveal hides in plain sight, in a simple color change that screams space is getting bigger. Redshift works like this: light has colors, and stretching the space between adds more red to the mix. If a galaxy sends out a pulse of light and the distance lengthens while it is on the way, the color nudges toward red. It's a bit like listening to a note grow softer and lower as the source drifts away, but with light that softening comes as a shift in color. Think of a rubber band being pulled between you and a friend. The band stays taut, and the whole scene changes as you stretch. The big reveal arrives when many galaxies show a pattern. The farther they lie, the more they seem to retreat. The universe isn't a static stage, it is a growing canvas, and the redshift pattern reads like a map that points outward in every direction. Around us, there is also a faint glow left over from the birth cry of everything, the afterglow that whispers of a very hot, bright start that cooled over time. It's not a loud headline, but it is a steady clue that the cosmos began in a different, hotter moment and has been expanding ever since. Today, redshift is a practical tool. We use it to estimate how far away things are and how fast they seem to be drifting apart, which helps us sketch the big shape of the universe. Looking at light from far away is like looking back in time, because the journey itself takes real time. The result is a simple, human story. The universe grew from a crowded, hot start, and everything since then has been stretching along with it. A cosmic treadmill keeps turning, and we ride along, curious and a little awed, savoring the view as space keeps widening the stage.